Hi everyone, today we're looking at parametric equations, which is 15F. When you have a curve on a plane, you should know how to describe its curve using its Cartesian equation. So we looked at straight line polynomials and recently uh, circle, ellipses, and hyperbolas. Um, Another technique to express those coordinates instead of using Cartesian ones is what we call a parametric curve. So what we have is those both x coordinates are a function of a third variable, um, where t is called the parameter of the curve. T is usually described a time variable. And those are the examples. So the left hand side you should be familiar with. For circle, ellipse, and a hyperbola, those are your Cartesian equations respectively, and we can express them as a parametric equation by having x and y having those equal to those functions, and that's what you need to be familiar with. So for a circle, and it's easy to demonstrates once you know your trigonometric identities. If I do the Cartesian equation, it's x squared plus y squared equals r squared. So the center is at the origin. The right hand side squared is your radius. We can express that x and y being a product of the radius by respectively cos of t and sine of t. If we square those two and we add them together, we remember the identity cos squared plus sine squared equals 1. That will simplify to r squared. Ellipse, very similar to a circle, except the first coefficient is not the radius this time. It's going to be the square root of the denominator of the respective x and y. So a to x and b factor for y. Now, if a and b were equal, you will end up to be a circle. So what happens is a circle is actually a particular situation of an ellipse, and it's something to remember. For a hyperbola, is remember it's minus, it's a difference at e equals to 1. You have your those respective formula. So x equals a times sec of t, which is the reciprocal of cos, and y equals b times tangent of t. So that's a summary of the common parametric equations that we'll be using. Also, you can be given some other parametric curve, and by using this technique, which is trying to eliminate the t parameter, to recreate a Cartesian equation and trying to make y the subject, that Cartesian formula or rule can tell you what does the curve look like instead of having the parametric curve. And we'll do a few examples on that. Alright, so this one without a transition, just alright, so those are the two questions. So you have your parametric equations. You need to find the Cartesian equation, and the next one is you need to find a parametric equation for a line through the point A and B. So here you just determine your standard Cartesian equation y equals mx plus c. Alright, so with part A, what you do is you use either equation, the ones that are the simpler to make t the subject. So with the first one, you make t the subject and you substitute into the second one. Here is your substitution. You simplify and you get the equation of a straight line. Okay. Next one, going backwards, you determine your equation of a straight line. That should be something you should be familiar with. Determine your gradient. use this expression or the y intercept form, you end up with this straight line. Now, to create your parametric equation, so what you do is you define either x or y being your parameter. So you simply state x equals t. So this is very subjective. It's a choice. You choose to make this one here, and you substitute into the expression of y to express y in terms of a t. So depending on how you do your assignment here, you may have a different parametric equations than each other. Alright, so here you have your parametric equations. So I would pause the video trying to determine the Cartesian equation, and we're just going to continue. So here you have looking at here the first equation is the simpler expression to make t the subject, which you rearrange, you substitute into the second equation to get this Cartesian form, which is a parabola. Alright, next one, so it's a little bit, this one we're going to be involved with circles. So here you have your parametric equations of a circle, something that without changing into a Cartesian form, it's actually, once you get used to it, it's easy to determine the features of a circle. So for a circle, you need to get the coordinates of the center and the radius of the circle. Here, the values that you add respectively to x and y will dictate your translations, but also the center of the circle. So the center has the coordinates 1, -2. The coefficient in front of cos and sine is a 1, so the radius is equal to 1. With this one, you should be more familiar. The center is -1, -3, and the radius is a square root of 4, which is 2. So with the first one, what you need to do is you need to rearrange each equation to make cos and sine the subject respectively, which is what we obtain down here. And you use the Pythagorean identity. So when you do the sum of the squares, that equals to 1. Now the cos and sine, we use the expression that we have rearranged earlier, and that is going to be equal to 1, and that gives you the equation of your circle. This is going to be the same principle with the parametric equations of an ellipse, because remember, an ellipse is a general situation that includes circles. Alright, with part B, you have what we do is you should make it equal to 1. So you divide everything by 4, and you include the 4 inside those squares, so that becomes a 2 because 4 equals 2 squared. So that will be x plus 1 over 2, y plus 3 over 2. That's how you obtain those ratios, and we make each one of them respectively cos and sine, because that would be equal to 1. Once you have that, you make x and y the subject, and you get your parametric equations. Same with the parametric Cartesian equation of an ellipse, which is already simpler because already you have the right hand side is equal to 1. Anyway, we'll get there in another example. So here we have the ellipse, so you have your parametric equation. So here you make cos and sine the subject. You use the identity that the sum of the squares is equal to 1, and that gives you your sum of squares is equal to 1. We want, that's the ellipse, so that's fine, you leave it like that, and I will give you the final equation. So the center of the ellipse is 1, -1, and your A, which is horizontal, and your vertical, which is your B, your A is 3 and your B is 2. Alright, with part B, so that is equal to 1. So you use the Pythagorean identity, and you substitute this by cos squared and sine squared. So we have cos and sine. We rearrange to make x and y the subject, and we end up with those parametric equation of that ellipse. We can do the same again. It's a little bit repetitive, but this time is for a hyperbola. So as a hyperbola, the x will have a sec of t. So a reminder, sec is the reciprocal of cos, so it's 1 over cos, and the y is going to be tangent. Now you're not going to use the Pythagorean identity, you're going to use the other identity, which is 1 plus tangent squared equals sec squared. So what we do for part A is we make sec and tangent the subject, okay, and the difference of those squares is equal to 1. So we substitute the expression with a minus, that equals to 1, and that is a familiar side of the equation of a hyperbola. So with this, with you hyperbola, how does the you have that and that. You can determine when you have, so the center of your hyperbola is going to be -1 and 2. When you have the equivalent of your old x-intercept, so you make y equals 2, your x will be on the left, a -3, on the right, a +3 from -1. So there's some familiar features here that we can identify as once you get from a parametric equation into a Cartesian form. Now you have a Cartesian equation. So what we need, it's a difference of squares equal to 1. So you need to have the left hand side to be your sec squared and the right hand side to be a tangent squared. So we do a substitution here. We rearrange to make x and y the subject, and we have the parametric equations. Right. This time is a little bit of determining what those parametric equations look like. So you need to eliminate the parameter, which is using the first equation. And as you substitute into here, you end up with y equals x squared, which is a parabola. Now, don't rush and graph it. What you need to pay attention to is how the domain for t is restricted. Because you restrict t between 0 continuously to 2, if you go back to your parametric equation for x, as t is between 0 and 2, it means that x will be between -1 and 1. So that is the domain for x. And to find the range, what you do is you just substitute the end coordinates into the Cartesian rule to find the y coordinates. So what we have here, so you can see it's a section of that parabola. Okay, so don't just pay attention to the details that is given in the question. Alright, last one. Find the point of intersection of the circle and the line defined by the parametric equation. Circle and a line, it's a points plural. A line, when it intersects, fully cut through a circle, it will be 2 points of intersection. So you need to find 2 points, 2 pairs of coordinates. So to solve that is you need to go back to the Cartesian equation. So a reminder here, you make, for the circle, you make cos and sine the subject, you square them, add them together, that equals 1. That will give you this equation. With this one, you make t the subject, you substitute in this one, and that gives you this straight line. You make you substitute that y expression into the equation of a circle, which you get here. That's the original form. You expand the bracket and you try to factorize. Once you factorize, you use the north factor law. We end up with those two coordinates, x coordinates. We substitute into the equation of a straight line, which is easier to find the respective y coordinates, which are over here, and we can write the points of intersection. Visual representation. Again, when you look at the parametric equation, the circle has no translation, so the center is the origin, the radius is 5, so you have your red circle, center at the origin. Your equation, let me remember, the Cartesian equation is 2x minus 2, so it's a gradient of 2, negative 2 is your y-intercept, and you have your 2 points of intersection with the coordinates. So that's, if you were asked to do a graph, there is the things that you would have to annotate, so the position where it intersect and the exact coordinates. And that's it for today. See you later.